Hello guys, in this very lesson, we are going to continue working on horizontal uniform circular motion under complex derivatives. And today, we are looking at a car moving in a banked circular path or a bike rider moving on a circular path. Now, in our previous two previous lessons, we looked at a canonical pendulum, and after that, we looked at a car simply moving on a plain circular path. So today we are looking at what it's going to look like when a car moves in a banked circular path. This is not a plain circular path. So let's quickly have a pictorial diagram. I'll try my best to draw this. I'm not really very good at drawing by heart. I could draw well, but not by heart. So we have this. So let's say this road, this very circular path. Let's say we have some ice on it. Let's say it snowed and we have some ice on it. So let's say this very ice on this road, mount on the road like this. You just have a feel of the road like this, and then we have a car traveling on this circular path. Now, when we talk about banked, to be banked simply means a portion of the road is being raised inward towards the center of the road. It's not raised outward, it's raised inward. So this is banked. Banked simply means it's being raised in such a way. Now, the reason why we have the scenario, don't forget that in our previous lesson on a car moving just on a plain circular path is the frictional force on the tires that helps that very car to maintain circular motion. But in this scenario, in this case, frictional force is not needed, and that's the reason we have the banking. It's the banking that helps us achieve that circular motion. When we talk about banking, we're talking about just the normal reaction as a result of the banking. So yeah, frictional force is not really considered. So when we have this, let's say we have a car. Let me try my best to draw this. Let's say we have a car like this at this point. We have a car. We have a car like this. Oh, so we have a car like this. Quickly, you say we have a car. And we have the road. What a wonderful car. I have a car like this. There's the mirror of the car. So yeah, so let's say we have a car. These are the tires. Wow, what a car. So let's say we have a car now. As you can see, this very car is moving on this banked road. The road is not a plain road. It's not a plain circular path, so it is banked. So for the fact that we have this very car moving on this banked circular path, now this car is banked, and as you can see, there's a kind of angular motion. You have angular movement here, unlike the other one that is plain. So the movement here is angular. So this car keeps moving like this on this banked surface. So now, how do we explain this? Friction is not what really helps us attain centripetal force here. It's not friction. What helps us to get centripetal force here, that keeps this whole thing in motion, is what we call normal work. It's normal force or reactive force. Normal force or reactive. Normal force or reactive force equals to centripetal force. That's what we have, equal to centripetal force. So this whole thing at a given angle theta. So now don't forget there's a weight for this very body that goes this way. So, but you're not going to focus on that really. You're going to be focused on normal force. So there's a normal force like this. There's a normal force that goes like this. There's a normal force like this. Fm. So this normal force acts at a given angle against the horizontal. Although we have a weight acting down like this. There's a weight acting down like this. A weight acting across. I'm sorry for my diagram, but there's a weight acting down like this. Or you have a normal force acting. There's a normal force that keeps this body moving in the circular path. So this normal force is at angle theta against the horizontal. So for the fact that we have a normal force that goes like this, the normal force could be resolved in two dimensions. We have theta here, a normal force in two dimensions, like this, and like this. So we have a normal force along the y-axis and normal force along the x-axis. This is the angle. So what do we have here? This opposite hypotenuse. So the normal force along x-axis is normal force times, what it is, Normal force times sine theta. That's that. And normal force along the y-axis is normal force times, what do we have? Normal force times, nice, normal force times cos theta. So Katua, very important. Opposite hypotenuse, adjacent. Adjacent of hypotenuse is cosine. So we have this set out. As simple as that. So what do we do next? What do we have next? Now let's compare. There's a weight, a direct weight from the center of this very car moving in a banked path like this. So when we have sum of forces along y-axis, which is mass and acceleration along y-axis, acceleration along y-axis is zero. There's no movement along y-axis. We know that. The sum of forces along y-axis is 0 Newton. There are no, all the forces along y-axis will cancel out each other because there's no movement along the y-axis. This is horizontal uniform circular motion. That's what we are discussing. So what are the forces we have? We have the normal force, the Fn, minus the direct weight. There's a direct weight here, Fw, equals to 0 Newton. So we have Fn minus gravity, mass times gravity, 0 Newton. So the normal force along the y-axis, I beg your pardon, is this mass times gravity. This is normal force along the y-axis. So quickly, when we look at the normal force along the x-axis, the normal force along the x-axis is what brings about, how will I call it? It's what brings about the major movement. As you can see, we have a force moving like this. So this normal force here, you have a force going like this. So it's this very normal force that keeps this body moving in this very circular path. That's normal force along the x-axis. Apart from this normal force along the y-axis that is opposing the direct weight, the weight of this very moving car. So now let's look at forces. Sum of forces along the x-axis. Sum of forces along the x-axis equal to mass times acceleration along the x-axis. It's along the x-axis that we have the main acceleration. So which is centripetal acceleration, either this or this. I like it as alpha. So this, which is v squared over r. As simple as that. So what do we have? We have this. So we have normal force along x-axis equals to mass times v squared over r. So normal force along x-axis is mv squared. It's very much like the canonical pendulum. It's very much alike. So we have everything set out. So what do we do? Just bring them, over one another, over each other, beg your pardon. So this over this, normal force along x, normal force along y, which is what we have, Fn x over Fn y. By the time you put them over each other, you're going to have tan theta, just like canonical pendulum, equals to, what do we have? The Fnx is mv squared over r divided by mg, just the same thing, very much like the canonical pendulum, tan theta. So you end up with mv squared over r times 1 over mg. So tan theta is equal to v squared over g r. So this is just it. So the angle of movement, we got the banking of the angle, the banking angle theta. So the tan of the banking angle is got the speed square of the linear speed of this whole thing times gravity times the radius of the circle. So that's just that for everything. That's that for now. Don't forget, even somebody, let's say a bike rider, somebody riding a bike on a plain road, it's the same, very much the same scenario. You're going to end up with this, just the same thing. So that is that for this very lesson. So we're going to call it a day here for this very lesson. So if you have found this lesson helpful, please follow me on Facebook, a Revelation of. Also, subscribe to this very channel, Edu Mosaic, and share this lesson with others. See you in the next lesson. Thanks.